Hello students, today we revise the velocity triangle of Pelton wheel. This is the nozzle. The water leaves from the nozzle with the velocity of V1. The water leaves from the nozzle with the velocity of V1. That means V1 is the absolute velocity of water jet at inlet of turbine. That absolute velocity of water jet has the two components. The first one is the horizontal component, second one is the vertical component. That means we resolve the absolute velocity v1 in two parts. First one is the horizontal component, second one is the vertical component. Already you know that the horizontal component is the v1 cos alpha and vertical component is the v1 sin alpha. The alpha is the angle made by the absolute velocity v1 with the horizontal direction. That alpha is also nozzle angle. That alpha is also called as nozzle angle. So v1 cos alpha is the horizontal component, that is the whirl velocity at inlet. That is the whirl velocity at inlet. And the vertical component v1 sin alpha, that is the flow velocity at inlet, that is the Vf1, flow velocity at inlet. So every velocity component is the resolved into two parts. One is the horizontal and one is the vertical. And horizontal component is the whirl velocity and vertical component is the flow velocity. So here V1 is the absolute velocity and horizontal component is the whirl velocity Vw1 and vertical component is the Vf1. This blade is moving in this direction with velocity u. So u is equal to the u1 is the velocity of the blade at inlet. This is the u1 velocity of the blade at inlet. Relative velocity is equal to v1 minus u1. Relative velocity is the v1 minus u1. So this is the relative velocity is in the direction of the blade angle. This relative velocity is in the direction of the blade angle theta. That means theta is the blade angle at inlet. Theta is the blade angle at inlet here. Theta is the blade angle at inlet here. So VR1 is the relative velocity at the inlet and U1 is the blade velocity at the inlet. And already you know that the VW1 is the whirl velocity component and Vf1 is the flow velocity component. That water leaves with absolute velocity v2. That water leaves the absolute velocity with v2. That is, that v2 is resolved into two components. First one is the horizontal component and second one is the vertical component. That horizontal component is the v2 cos beta, v2 cos beta, and that vertical component is the v2 sin beta. And horizontal component is the whirl velocity and vertical component is the flow velocity. So the vertical component is the flow velocity Vf2, that is v2 sin beta, and horizontal component is the Vw2, that is v2 cos beta. And that beta is the angle made by absolute velocity at outlet. That beta is the angle made by absolute velocity at outlet. So this is the relative velocity is in the direction of blade angle at outlet. Is in the direction of blade angle at outlet. The blade angle at outlet is the phi. The blade angle at outlet is the phi. That is equal to, that phi is equal to 180 minus delta. 180 minus delta. That delta is the angle of deflection. This is the angle of deflection. So Z angle, see here phi is equal to phi. That phi is equal to 180 minus delta. That delta is the angle of deflection. So this is the your VR2 and the angle made by the VR2 with the horizontal is the phi. Phi is the blade angle at outlet. So VR2 is equal to V2 minus U2. So this is the U2, blade velocity at outlet. This is the blade velocity at outlet. But in Pelton wheel, the nozzle is horizontal. So the angle made by absolute velocity V1, that means the water jet is the 0. that means water jet is equal to the 0, that alpha is equal to 0, that alpha is equal to 0. So what will be happen? The alpha is equal to 0, that means V1 is equal to VW1. That means V1 is equal to VW1, because that alpha is equal to 0 means that V1 line is overlap on that VW1. That V1 line is overlap on the VW1. So V1 is equal to VW1, and the relative velocity is equal to this much. The relative velocity is equal to this much, and VF1 is equal to 0, and VF1 is equal to 0. So see here, V1 is equal to VW1, and this is the U1, and this is the VR1, and VF1 is equal to 0 because alpha is equal to 0, because alpha is equal to 0. Nozzle angle is equal to 0 because nozzle is a horizontal, That's why inlet velocity triangle is a straight line in Pelton wheel. That's why inlet velocity triangle is a straight line in Pelton wheel. We revise the inlet velocity triangle once again. This is the V1, that is the jet velocity at inlet of the turbine through the nozzle. Jet velocity at inlet of the turbine through the nozzle. That V1 has two components. One is the horizontal and another is the vertical. That horizontal component is the whirl velocity, that is equal to V1 cos alpha, and that vertical component is the flow velocity, that is equal to V1 sin alpha. That is the V1, that is VW1, that is VF1. Okay. After that, that blade is moving with the horizontal direction with velocity u. So this is the u1 is the blade velocity at inlet, and you know that VR1 is equal to V1 minus u1. So this is the VR1 at the angle of the blade angle at inlet, at the angle of the blade angle at inlet. So remaining one is the VW1 minus u1, this u1 this much. This is the velocity triangle when the beta is less than the 90 degree. When the beta is less than the 90 degree. There are three cases when beta is less than the 90 degrees. First one, when beta is equal to 90 degree, is second one. When beta is equal to greater than 90 degrees, third one. Just see that cases. First case is the beta is less than 90 degree. How you can identify beta is less than 90 degree? When VR2 cos phi, VR2 cos phi is greater than U2, that means beta is less than 90 degree. When VR2 cos phi is greater than U2, that means beta is less than 90 degree. So we previously see the velocity triangle of Pelton wheel, that is similarly for beta is less than 90 degree. Okay, next one is the beta is equal to 90 degree. Beta is equal to 90 degree. If VR2 cos phi is equal to U2, at that time beta is equal to 90 degree. When VR2 cos phi is equal to U2, at that time beta is equal to 90 degree. You calculate VR2 cos phi, that value is equal to U2, at that time beta is equal to 90 degree. Inlet velocity triangle is the same, it is straight line, it is same, it is not changes. So beta is equal to 90 degree, that means that beta is equal to 90 degree means it is overlap to the VF2, it is overlap to the VF2 here as it is. That means V2 is equal to VF2 when beta is equal to 90 degree, and that VW2 is equal to 0. That VW2 is equal to 0 because that V2 is overlap over the VF2 when and when only the angle beta is equal to 90 degree here. That V2 is overlap over the VF2, at that time beta is equal to 90 degree. That means V2 is equal to VF2, beta is equal to 90 degree, and that VW2 is equal to 0. VW2 is equal to 0, and VR2 as it is, and VR2 is in the direction of blade angle at outlet, and that angle is equal to phi, and this is the U2. This is the U2, blade velocity at outlet. Third case is the beta is greater than 90 degree. When beta is greater than 90 degree, if the VR2 cos phi is less than U2. When solve the problem, at that time you calculate VR2 cos phi, that value is less than U2, then and then only beta is greater than 90 degree. Beta is greater than 90 degree. Beta is greater than 90 degree, that means here beta is less than 90 degree. Up to this point beta is equal to 90 degree, and from here beta is more than 90 degree. From here beta is more than 90 degree. In case of beta is less than 90 degree, at that time phi2 is in this direction, and in this position phi2 beta is equal to 90 degree. At this position beta is greater than 90 degree. This is the angle beta is greater than 90 degree. That means this is the phi W2, this is the as it is Vf2, and this is the phi2, and this is the phi R2. VR2 is equal to phi. Phi R2 is the angle made with phi. So phi is the blade angle at outlet. Blade angle at outlet, and VR2 is the relative velocity at outlet. So phi R2, in between the velocity phi R2 and V2 is the velocity U2, and this is the velocity phi W2, because phi R2 is equal to phi2 minus U2. That's why this is the U2 and this is the phi R2. Let us see the problem. The Pelton wheel is receiving water from penstock with a gross head of 510 meter. 1/3 of gross head is lost in the friction in the penstock. The rate of flow through the nozzle fitted at the end of the penstock is 2.2 meter cube per second. The angle of deflection of jet is 165 degree. Determine the power given by water to the runner. Power given by water to the runner. Second one is the hydraulic efficiency of Pelton wheel. Take CV is equal to 1.0. Speed ratio is equal to 0.45. You can also read the question that is displayed on your screen. Once again, the Pelton wheel is receiving water from penstock with gross head of 510 meter. That means gross head HG, H suffix G, is equal to 510 meter. 1/3 of gross head is lost in the friction in the penstock. That means friction head HF is equal to 1/3 of gross head. The rate of flow through the nozzle fitted at the end of the penstock, that is Q, is equal to 2.2 meter cube per second. The angle of deflection of the jet is equal to 165. That means delta is equal to 165. And the power given by water to the runner. Power given by water to the runner. That means the runner power. That means the runner power. And second one is the hydraulic efficiency of the Pelton wheel. Coefficient of velocity is given 1. Speed ratio KU is equal to 0.45. So write down the given values. Gross head 510 meter. Friction head is the 1/3 of gross head, means 1/3 of 510. That is equal to 170. That is equal to 170. The flow rate is given 2.2 meter cube per second. Angle of deflection delta is given 165. So blade angle at outlet phi is equal to 180 minus delta. That means 180 minus 15 is equal to the 180 minus 165. 180 minus 165, that is equal to 15 degree. That is equal to 15 degree. That means blade angle at outlet is equal to 15 degree. So coefficient of velocity is equal to 1. Speed ratio K suffix U is equal to 0.45. We have to find out runner power and hydraulic efficiency. First one, we have to find out the power given by water to the runner. The power given by water to the runner, that means runner power. For that, find out the velocity of jet phi1. Phi1 is equal to CV square root of 2gh. That's V's coefficient of velocity is given 1, square root of 2gh means 2, g is the acceleration, 9.81, h is the head. We have to find out the net head. That net head is equal to gross head minus friction head minus head above the head below the nozzle minus head below the nozzle. The head below the nozzle is not given in most of the times. At that time it is equal to the 0. At that time it is equal to 0 or neglected. So h is equal to hg minus hf minus h. That hg is gross head, hf is friction head, minus h is the head below the nozzle. That when the head below the nozzle is not given, most of the time it is not given, it is assumed as 0 or neglected. Only write down the formula. H is equal to hg minus hf, 510 minus 170, that is equal to head on the turbine, h is equal to 340. Put the value of h here, so we get the V1 is equal to 81.674 meter per second. Next one is the velocity of the field. U is equal to k speed ratio k suffix u square root of 2gh. Ku is equal to 0.45, 2, g is the acceleration, 9.81, h is the 340. That velocity of the field at inlet and outlet, that is equal to 36.753 meter per second. After that, draw the velocity triangle. For normally beta is less than 90 degree. For normally beta is less than 90 degree. From inlet velocity triangle, VR1 is equal to V1 minus U1. VR1 is equal to V1 minus U1. So VR1 is equal to this much. Also we know that V1 is equal to VW1. V1 is equal to VW1, that is equal to 81.67 meter per second. 81.67 meter per second. From outlet velocity triangle, we have VR2 is equal to VR1 is equal to 44.92 meter per second. Because VR2 is equal to VR1, because blade friction coefficient K is not given, that means blade friction coefficient K is equal to 1, that means VR2 is equal to VR1 44.92 meter per second. So cos phi from outlet velocity triangle, cos phi is the adjacent side upon hypotenuse. Adjacent side upon hypotenuse. That adjacent side is the U2 plus VW2. U2 plus VW2, and hypotenuse is the VR2. So cos phi is equal to U2 plus VW2 divided by VR2. Put phi is equal to 15 degree. VR2 is equal to 44.92. U2 is equal to 36.75. Already we find out. So VW2 is equal to 6.64 meter per second. So power given by water to the runner, that is equal to runner power is equal to rho A V1 VW1 plus VW2 into U. Okay, and A V1 is the discharge or flow rate Q. So rho Q VW1 plus VW2 into U. When beta is less than 90 degree, we know that here plus sign. So rho is equal to 1000, Q is equal to 2.2, and VW1 81.67, VW2 6.64, and U is equal to 36.75. So we get the value 7139863 watt. So convert it into kilowatt by multiplying 10 raised to minus 3. By multiplying 10 raised to minus 3, we get 7139.863 kilowatt. That is the runner power, or power given by water to the runner, is equal to 7139.863 kilowatt. Next is the hydraulic efficiency, that is equal to twice of VW1 plus VW2 into U square root of V1 square divided by V1 square. 2 VW1 plus VW2 into U divided by V1 square. So put the value of VW1, VW2, U and V1 and we get the answer 0.9371. 0.9371, that is equal to 93.71%. 93.71%. 93.71%, that is the hydraulic efficiency. Thank you.